Right, so far our notion of graphs has been defined as follows. We have a finite set of vertices and a finite family of unordered pairs of vertices that we call edges. This is great, it's useful in many applications, but sometimes you need things that are variations of this notion. And the first variation we will consider is a digraph or a directed graph. So the only difference between a digraph or a directed graph is that instead of saying that our vertices, our edges are unordered pairs, we require them to be ordered pairs. And we call them arcs, but this is just a difference of name. It's not so much to worry about, and some authors call arcs edges and so on. So let's look at an example. So let's look at an example where we have D as follows. The vertices of D are 2 points, X and Y, and the arcs, or if you wish, edges of D is the ordered pair X, Y. So how does this look like? You have two vertices X, Y. Ordered pair means that XY is not the same as YX, and the way this is indicated is by an arrow from X to Y. So this is the formalism behind such graphs where we have direction in the graph. So sometimes to save space, instead of writing bracket x comma y bracket, you just write it at xy and you say that it goes from x to y. And so note that xy is not the same as yx. So this is xy and this is yx. Now, let's look at a specific example of digraph. So let's look at the digraph D, which is the following. You have, or let's call it D1. So let's look at two examples of digraphs to illustrate some important notions. So let me look at the graph D1, which looks like this. And the graph D2, which also looks like this. But now I'm being stupid, I forgot the directions, so maybe let's say that this graph has these edges and this graph has these edges. So, or arcs. So the arcs of D1, this is the arc going from X, Y, and it's counted twice. And the arcs in D2, now we have xy together with yx, because one arc is going this way, the other is going the other way. And now remember, xy and yx are not the same. So really, apart from the order, apart from the direction on the arcs, these are the same graph. And the way to deal with this is to define the notion of an underlying graph. So the underlying graph of a digraph is the usual, meaning undirected graph, we obtained by forgetting the order or erasing the directions on the arcs. And you call a digraph simple if it has no loops and multiple arcs. But beware, a digraph can be simple even if the underlying graph is not simple, and a simple digraph can have the same underlying graph as a non-simple digraph. This is a very confusing sentence. Let's see what it actually means. Let's go back to our example. So the underlying graph, if we forget about the arrows, is not simple because we have a multiple edge between x and y. But if we now look at them as digraphs, D1 is not simple because the arc xy, meaning the arc going from x to y, there are two such arcs. D2 is simple because it doesn't have multiple arcs. It has xy and yx, but these are not the same. xy goes from x to y, yx goes from y to x. So this illustrates this notion that being a simple digraph can happen even though the underlying graph is not simple. Now, what is an isomorphism of digraphs? An isomorphism of digraphs is the same as an isomorphism of graphs. So it's an isomorphism of the underlying graphs, but also preserving the order. So let's look at the following examples. Let's look at this digraph. This digraph. And this digraph. Let's label the edges, the vertices. Now, which ones of these are isomorphic as digraphs? Obviously, if you forget about the order, these are all exactly the same underlying graph. So as undirected graphs, they are all isomorphic. They're all exactly the same. I've just renamed the vertices. But now, how can I produce an isomorphism of digraphs? Well, I claim that these two are isomorphic, and the isomorphism sends D, which is the vertex that everybody's running away from, to H. E has one incoming, one outgoing, and it goes to G. Properly speaking, Y and F goes to I. Why is this an isomorphism? It is an isomorphism because between any two vertices here, I have an arc in the right direction, precisely if I have an arc in the right direction here. So I have an arc from D to E, and I have an arc from H to G. I have no arc from E to D and no arc from G to H, and so on. So I'm preserving, I'm mapping the vertices here to vertices here in such a way that there is an arc from a vertex to another vertex, if and only if the same is correct for the graph where I'm going. So I'm mapping the vertices, paying attention to the order of the arcs. This graph, the first one, is not isomorphic to these. Why is that? Well, if you look here, this graph has the vertex F, where both arcs are directed towards F. So it has a so-called sink. It's a popular vertex where everybody wants to be. So everybody's rushing toward F here. And I have no such vertex here. So there is no way I can map the vertices of my graph to the left to the vertices here so that I get such a popular graph F. I will always have all my vertices having one arc going in, one arc coming out. So they are not isomorphic. A way to make this precise is to talk about degrees of vertices. So in a regular graph, you had the degree as the number of edges that connect to the vertex. In a digraph, you separate edges into edges or arcs coming into the vertex and arcs going out from the vertex. And the number of such arcs are called in degree and out degree. As you notice, I am using the word edge instead of arc. You can either say this was a mistake on my part or just an alternative usage of words. In a digraph, you use the words edges and arcs alternatingly. So if you go back to this previous example, what I was saying was that in this graph, every vertex had in degree 1 and out degree 1. Here I had F with in degree 2, out degree 0, and therefore it's not possible to construct an isomorphism because I will not be able to find a vertex of the right in and out degrees to map to F. So let's look at another example. So here, let's look at something like that. So if I have this vertex X, then the in degree of X is 2 because I have 2 arcs or edges directed towards X, and the out degree of X is 1. And in the same way, you have a directed handshaking lemma. So that's the directed analog of the ordinary handshaking lemma. And in fact, it's more intuitive than the regular one. So it says that the sum of all in degrees equals the sum of all out degrees. So it's intuitive because every edge has to start somewhere and end somewhere. So you have as many starting places as ending places. And so for every place where your edge contributes to the in degree, there will be another place where the edge contributes to the out degree. If you move around between houses, you will enter as many houses as you will have left. Otherwise, you have cloned yourself. As for ordinary graphs, you have matrix representations of digraphs. So for ordinary graphs, we looked at adjacency matrices and incidence matrices. Here we only look at adjacency matrices. So the adjacency matrix of a digraph with n vertices numbered from 1 to n is the matrix where the ij entry is the number of edges from vertex I to vertex j. In an ordinary graph, this was just the number of edges between these two vertices to cool, but now we make a difference between starting and ending vertices. So let's look at the following example. So I have vertices numbered 1, 2, 3, and let's direct our edges like that. The loop, directing a loop doesn't make much of a difference, but you put a direction anyway, because this is going to be the edge 3, 3. So it doesn't matter which 3 I write first and which 3 I write second. So what is the adjacency matrix of this graph? Well, take a moment to guess and we'll look at it together. Okay, so I have my vertices 1, 2, 3 and my vertices 1, 2, 3. So I have no edge from vertex 1 to vertex 1. I have 2 edges from vertex 1 to vertex 2, no edge from vertex 1 to vertex 3, no edge from vertex 2 to vertex 1. So the matrix is no longer symmetric. I have no edges going back here, no edges from 2 to 2, 1 edge from 2 to 3. From 3, I have no edges to 1, no edges to 2, but 1 edge from 3 to 3. And now those of you who remember the adjacency matrix of a regular graph might protest and say that I told you that loops counted as 2. Well, they do in an undirected graph, but in a directed graph, I am only going in one direction, right? Now, I don't have the clockwise counterclockwise option, so there is only one path from 3 to 3 of length 1, which is this one loop at one edge going from 3 to 3. So this is the adjacency matrix of this diagram.